Today's topic is the Hall effect. Objective is to determine the carrier density and the carrier mobility in germanium. The apparatus used were a Hall probe and the Hall effect apparatus, an electromagnet which has a model of EMU75 or EMU50Y, and constant current power supply with a Gauss meter, which is DGM102. The procedure were as follows: the widthwise contacts of the Hall probe with GE crystal were connected to the terminals marked voltage, and the lengthwise contacts were connected to terminals marked current. The Hall effect apparatus was switched on, and the current IX it was adjusted to a few milliamperes. The display was switched over to the voltage side, and note, any voltage reading observed outside the magnetic field due to the imperfect alignment of the probes for contact is identified as the zero field potential. After that, the probe was placed in the magnetic field and the electromagnetic power supply was switched on. The current was then adjusted to the desired value. The Hall probe was adjusted until it became perpendicular to the magnetic field, allowing the Hall voltage to reach its maximum peak. The Hall voltage is measured for both directions of the current and magnetic field, resulting in four observations for a particular value of current and magnetic field. The Hall voltage was measured as a function of current Ix, while the magnetic field Bz was kept constant at Bz 50 G or 100 G. After that, the Hall voltage was measured as a function of the magnetic field while keeping a suitable value of current constant at Ix equals to 3 milliamperes. The equipment system was switched off immediately after the experiment was completed.
Okay, to kick off the data analysis, we start by making the least square method table, which contains the magnetic field as X and the average voltage as VH. And the average voltage we got um, through averaging the voltages we obtained from the experiment. So here we have our graph. Again, we plotted um, the magnetic field against the voltage, and as you can see we have a straight line. So our next step is to obtain the slope and the intercept, and since we used the least square method, this is how we obtained it. We just followed the equations accordingly, and the result was VH equals minus 0.01615 multiplied by the magnetic field plus 83.916196. And then, of course, we went ahead and got the uncertainties for both the slope and the intercept. And again, just plug them with the slope we obtained first and the intercept. Our next task in the analysis was to get the Hall coefficient RH, and we derived the equation first from VH. We said it's equal to RH multiplied by the current multiplied by the magnetic field over D, and then VH equals I multiplied by the magnetic field multiplied by RH over D, um, and the slope equals VH over the magnetic field, and meaning it equals RH or multiplied by the current over D. We got this equation, and from that we got the RH, and this RH helped us determine the majority type carrier, whether the crystal is N-type or B-type, and since the RH is lesser than 0, that means it's an N-type crystal. Now we move to calculating the charge carrier concentration. N. RH equals 1 over NE, N equals 1 over RH E, um, and then just plugging the values. We also calculated the carrier mobility mu. Okay, now moving on to questions. What is the Hall effect? The Hall effect is the generation of a transverse voltage, the Hall voltage, across a conductor or semiconductor when an electric current flows through it in the presence of a magnetic field perpendicular to the current. When charge carriers move in magnetic field, they experience the Lorentz force, which causes them to accumulate on one side of the sample. This change, separation, creates an electric field and hence a measurable pole voltage. What are N-type and B-type semiconductors? N-type semiconductors are formed by doping a pure semiconductor with pentavalent impurities such as phosphorus or arsenic. Majority carriers are electrons, minority carriers are holes, and Hall coefficient is negative. On the other hand, the B-type semiconductors are obtained by doping with trivalent impurities such as boron or gallium. Majority carriers are holes, minority carriers are electrons, and Hall coefficient is positive. Third question, what is the effect of temperature on the Hall coefficient of a lightly doped semiconductor? For a lightly doped semiconductor, increasing temperature generates more electron-hole pairs. An increase in carrier concentration causes the Hall coefficient to decrease. At sufficiently high temperature, intrinsic carriers dominate and the Hall coefficient decreases rapidly. Therefore, the Hall coefficient decreases with increasing temperature. Question number 4 asks, do holes move? Yes, a hole is an absence of an electron is in the valence band. Although no physical particle called a hole exists, electrons from neighboring bonds continuously move to fill the vacancy, causing the vacancy itself to appear to move. Thus, holes behave as positively charged mobile carriers. They move in the direction of the electrical field and contribute to electrical conduction in B-type semiconductors. Next question, we are asked to show N or B equals to magnetic field multiplied by the current over the voltage multiplied by D multiplied by E. Just a very simple calculations, and we just put equation into equation until we get the result. Why does the resistance of the sample increase with increasing magnetic field? When a magnetic field is applied, charge carriers experience the Lorentz force and their trajectories become curved. As a result, the effective path length of carriers increase. More collisions occur, mobility decreases, consequently, the electrical resistance increases, and this phenomena is called magnetoresistance. Why is high input impedance device generally needed to measure the Hall voltage? Hall voltage are very small, typically in the millivolt range. If the measuring instrument has low input impedance, it draws current from the Hall probe and causes loading effects, reducing the measured voltage. A high input impedance voltmeter draws negligible current, minimizes measurement error, and ensures the actual Hall voltage is measured correctly and accurately. Last question, why should the Hall voltage be measured for both current directions and both magnetic field directions? Measurements are taken for all combinations of current and magnetic field directions since reversing current and magnetic field reverse the Hall voltage polarity. Also, it offset voltages due to contact misalignment, thermoelectric effect, and zero field voltage remain unchanged, and averaging the four readings cancels the unwanted voltages.
Now I'm going to present the discussion for the experiment. When the moving free electrons with velocity v passes through a sample of subjected to magnetic field B, the electrons are forced towards one edge of the sample by the magnetic force. This leaves the positive charge at the other edge of the sample, resulting in the electric field and thus the Hall voltage. The charge concentration at both edges will build up until the electric force on the moving free electrons is balanced by the magnetic force on the electrons, resulting in the equilibrium. This is a diagram of the Hall effect in the metal strip. On the left is the Hall effect for negative charge carriers, and on the right is the Hall effect for positive charge carriers. The current Ix flowing through the sample is defined through this equation below, where E is the elementary charge of electron, which is 1.602 times 10 power negative 90 coulomb, N is the charge carrier concentration, Vx is the x component of charge carrier velocity, and A is the cross-sectional area of the sample. Knowing that the cross-sectional area of the sample is the product of the width of the sample and the thickness of the sample, rearranging the aforementioned equations give us this equation for carrier concentration N. The Hall coefficient RH gives the information about the sign of majority charge carriers, with its value being negative if the charge of the carrier is negative and its value being positive if the charge of the carrier is positive. It is defined in the equation below. Using both equations for carrier concentration N and Hall coefficient RH, we get this equation. This shows that Hall voltage VH is proportional to the Z component of magnetic field strength Bz. The linear graph of VH against Bz can be plotted to find RH. Knowing the sign of majority charge carriers through RH enable us to determine if the semiconductor sample is N-type for negative charge carriers or P-type for positive charge carriers. From the experiment where we use germanium sample, the Hall coefficient RH of the sample calculated using the graph of VH against Bz is negative 0.26916 meter cube per coulomb. The negative value of RH in this experiment shows that the sample used is the N-type germanium. With this value of RH, the charge carrier concentration N of the sample is 2.3191 times 10 power 19 per meter cube. The ratio of the velocity of the charge carrier to electric field strength, which is carrier mobility, can be related to conductivity with this equation. With the equation and also the equation for Hall coefficient RH, we can find that the carrier mobility can be calculated using this derived formula. From the experiment, knowing that the conductivity of germanium is 10 Siemens per meter, and using the value of RH calculated, the carrier mobility in germanium sample is 2.6916 meter square per volt per second. In conclusion, the carrier concentration of the germanium sample in the experiment is 2.3191 times 10 power 19 per meter cube. The carrier mobility in the germanium sample in the experiment is 2.6916 meter square per volt per second.